This is the topic of area, which is our first topic, which is under the curve. The concept of area, which is under the curve is this. Let's say this is our B, and the horizontal line will be our A. For example, we will draw a line like that. This will be our y of f of x. This will be our b, and then this would be our a. This shaded part will be our area of interest, which is in this part, what I mean is we will get the area of that part which we shaded. So let us draw a vertical strip. This is a vertical strip that we will solve later. So let's label this. In this point, this will be our x and y. And then the thickness of this strip will be our dx. The distance from here to the origin, which is here, will be our x, and then the height of this strip will be our y. That's it. That is the concept of area under the curve. So let us extract this vertical strip to here. As we all know, this is our dx and this is our y. This would be y dx. To integrate, this will be the integration of d of a y dy. The integration of a is just a y dx. I mean, this is x. So our limit would be from here to here to here. That would be our limit. So our limit is from b to a. That's it. This is our formula in getting the area under the curve. Our first example in area under the curve is find the area under the line which is y equals 8 minus 2x. This would be the graph of this problem. It should be like this, like that. If we can picture it out, it is triangle. So to get the area of this shaded part, this would be our horizontal strip here. I mean a vertical strip. In this point, this will be our x and y. And then this would be our dx. And then our limit is from the origin, which is 0 to 4. So this would be our x. And then the height of this horizontal strip is our y. To solve it, we extract our vertical strip our dx and then our y. To solve the problem, we will use the formula y dx. Our limit here is 0 to 4. And then our y, which is 8 minus 2x dx. And then we will get the derivative of this. So the derivative of 8 minus 2x is 8 minus 2 over 2x squared. Limit from 4 to 0. So we will cancel this out since it is just 1. So, we forgot the x. So we will just easily plug in our limits. It would be 8 times 4 and then 4 squared. Since our lower limit is 0, if we plug in 0 to our x, it will be 0. And if we plug in our x or x squared, it will be 0. So to simple it out and to lessen our problem, we'll just write 0. And our final answer is 16 SQ unit. And then I have another way to solve this type of equation, since our graph is in a triangle shape. As we all know, to solve the area of a triangle, it is 1/2 base times height. The area of this is, to solve the area of triangle is 1/2 base times height. So our base is 4, since the, what you call this is 4, the measurement is 4, and then the height is 8, right? So our base would be 4 and our height is 8, 1/2. To solve the area, 8 times 4 is 32, divided by 2 is 16. 16 square unit. That's it. That's how you solve if you found on your every problem, which is area under the line, and it is on triangle shape, you can use this, the formula on how to get the area of a triangle. Our next topic, which is area between curve, is, the concept of this is, let's say we have this, and then we have a line here. This would be the point and the other point. This is y f of x, y f of x. This will be our area of interest. So let's say here will be our point, which is x and y. Then we will draw a vertical strip. In this part, this will be our dx. And then the distance between the end of this thickness of our dx to the origin of our graph is rx. Let's say this would be our y1 and y2. And then this to this will be our y2. And from here to here will be our y1. That's it. So let's extract our vertical strip. This is our dx and our y1 minus y2. Y1 minus y2 dx. That's it. That is the formula on how to get the area between curve. This will be the example of our area between curve. Find the area between the curve y equals x fourth and y equals 5x plus 6. To draw a graph, we all know that x fourth is a parabola. So it should be like this. Wait, I'm so sorry for the drawing, guys. It should be like this, a parabola. And then y equals 5x plus 6 will be our line. Would be like this. Wait, let us extend this line. And we will label it. This will be our y1. This will be our y1. X to the fourth, and this line will be our y2, 5x plus 6. So we will put a point where they intersect. Wait, maybe -1, and then here. That is the point where they intersect. Then let's say here is the x and y. You'll draw a vertical strip. This part will be our area of interest, including that horizontal strip. And then this will be the limit since, which is 2, -1, since in that point they intersect, which the curve and the line intersect in -1 and 2. So that's the x from the x will be here, from the origin to the horizontal strip, and the thickness of this horizontal strip is our dx, and then the height of our vertical strip. I'm so sorry for the error, guys. I always confused on vertical and horizontal. This will be our y. And then let us extract this vertical strip here. This will be y2 minus y1 dx. To solve, this would be a equals the integral of y2 minus y1 dx. That will be the formula we will be using in solving this problem. So the integral of y2 is 5x plus 6 minus x raised to 4. Our limit is from -1 to 2. It's -1, I'm so sorry, from 2. To 2. And that does not forget the dx. So we will just simply integrate this. To integrate, 5x is 5 over 2x squared plus 6x minus 1/5 x raised to 5, limit from 2 to -1. So we'll just simply substitute it. It's just 5 over 2 times 2 squared plus 6 times 2 minus 1 1/5 2 raised to 5 minus 5 over 2 -1 squared plus 6 -1 1/5 -1 raised to 5 equals 20 over 2 plus 12 minus 32 over 5 minus 5 over 2 plus 6 1/5. Our area is 28. Our area is 18.9 square unit. That's it. That is our final answer in getting the area between curve. So we've already discussed the area between curve and area under the line. Sorry, I forgot. We will now discuss the concept of a polar plane or the polar curve. So this will be let's say this part is a quadrant of a circle. So let's say this is our sector. Put R. And this line, this is our polar curve. And then let's draw what we called it. It is like vertical strip like that, and this will be our R here, and it's small r, and our R here, and the thickness of this will be our d beta, and then this will be our beta 1, and then from here will be our beta 2. So let's extract this to here. Let's shade that. This will be our R here, R, and this will be our D peta. To get the area of this is 1/2 R squared D peta. That's it. It is R squared since we have 2R here, and then the thickness of this is our D peta. And then our limits will be from our peta 1, which is this. Let's put it here. Our peta number 2. Sorry, I blurred it out. Here, above. And then 1/2 R squared D beta. That's it. This is the formula on getting the area of a polar curve. This is an example of a polar curve. Our example is find the area of R equals 2 cos beta. So this is an example of our graph, and I'm sorry if it is full of imperfection. This will be our 0 degree, our 90 degree, our 180 degree to 70 degree. Wait. We will label this. So this will be our circle 1, 2, 3, and 4. This will be a 30 degree, 60 degree, 120, 150, 210 degree, 240. Here will be 300 degree, and lastly 330 degree. That's it. So we will plot this, but first we will draw up what you call that, a table, and our in here we will start from 0, 30 degree, 60 degree, 90 degree, 120, 150, 180 degree. R to 10 to 40 to 70, 300, 330, 360. So we will where's my calculator? Here. We will input our R. We will input our R in our calculator. Wait. This will be the instrument that we will be using to solve our table. So this should be in degree, and then we'll solve it. First is we will click this and this. We'll set our calculator in table. We'll input this to here. So 2 cos alpha x equals, should be 0 since we don't need any g of x. Our start is from 0. Our end is from our end is to 360, and our interval is 30. Enter. Equals. So that's it. This is the value of our r. Wait. We'll input this to our table and what will be written earlier. Our 0 here is 2. Our 30 degree is 1.7332, but we will just use the 2 decimal point. 1, 0, -1, -1.73, -2, -1.73, -1, 0, 1, 1.73, 2. That's it. In here, our r is 2 and our 0, 1, 2. Our first point should be here. Our 30 is 1.73, so the point should be somewhere here. Our 60 is 1. Our 90 is 0. Our 120 is -1. Should be here. Our 150 is -1.73. It should be over here. And 180 is here. Our 210 is 1.8, somewhere here. Our 240 is -1. It should be like this. And 0. Our 300 is 1, so it should be here. Our 330 is 1.73, so it should be here. And our 360 is here. Should be like this. It's like a bow. We formed a bow on our graph. So here we will write our formula, which is the integral of 1/2 r squared d beta. We have a limit here, which is 0 to 90 degree. But first, let's write our horizontal strip, but I want it here. So here, this is our horizontal strip. This is our area of interest. So from 0 to 90, which is pi all over 2. That's it. That is our limits. So for integral of beta over 2, 0, 1/2 2 cos beta squared d beta. We will cancel this. Wait. We will cancel this. And it will be this too. We will cancel out the 2. For integral of beta all over 2, 0 cos squared beta d beta. So that's it. We will input this on our calculator. Menu 1, but this should be on radian since we are dealing with angles. So shift radian for the integral of 0 to pi over 2 cos x squared. That's it. Our answer is pi. And that is our final answer. Pi square unit. That is our final answer. Let us now proceed to volume using integration. Volume using integration consists of disk method, shell method, and washer method. But first, we will tackle about the disk method. The concept of a disk method is when you draw a curved line here and your limit is here to B, we'll first draw a broken line here. And at this point, this will be our X and Y. And then in this point, we will draw a vertical strip. And this will be our area of interest. And then in this method, the area of rotation is here. That's it. That's how you plot your graph. And then we will draw our disk now. Like that. We will draw it from the vertical strip that we've drawn. And then we will label it now. The distance from here to here will be our X. And then the height of this will be our Y. To extract it out, this will look like this. And this part, this will be the area of rotation. This will be our Y. dv by y squared. The derivative of this is just b. The integral of pi y squared dx. And our limit is here from a to b. A to b. That's it. Our number one problem is determine the volume if the area under the line is y equals x. From x is to 0, from x equals 0 to x equals 2 is rotated about x-axis. So this will be our 0, and this part will be our 2. And this will be our area of interest. This is our area of rotation. In this point, this will be our x and y. And we will draw here our vertical strip. From this line to the origin is our x, and then from here to here will be our y. And then we will draw now our disk. That is our disk. Sorry for the drawing though. Then we will now extract our disk to solve it. And this part will be our area of rotation, and this will be our y. dv by y squared dx. V by y squared dx. And limits from 2 to 0. Let's put the pi outside since pi is our constant. The limits from 2 to 0, x squared dx. Let's integrate the x. X cubed over 3. Limits from 2 to 0. Pi. So pi times 2 cubed over 3 minus 0. Let's just, let's then 2 cubed. Our final answer is 8 all over 3 pi. That's it. That is our final answer. So we will now proceed to shell method. This is the sample graph. The concept of a shell method. Let's say this will be our y, this will be our x, and this line will be our y equals f of x. This part will be our a and our b, and this inside the a of b will be our area of interest. Let's say this will be our vertical strip. From this part to the origin will be our x. The height of this will be our y. Unlike the this method, our area of rotation is here, but in shell method, our area of rotation is parallel to the strip. So here, this will be the area of rotation in shell method. And then we will now draw our shell. It should be like this. It will look like that. The inside of our graph should be like this if we are using the shell method. It should look like a cylindrical tin can. So we will extract this cylindrical tin can to here. This is our y, height of the tin can, and in this part will be our area of rotation. And from here to here will be our x. To solve the area, this will be 2 pi x. The height of this is y. The inside is dv, and the thickness of this is r dx. So dv 2 pi xy dx. To derive the formula should be v, the integral of 2 pi xy dx. Limits from, is there any limits on shell method? I think yes, b to a. And this will be our formula. This will be our sample problem in our shell method. This is derived from the example of my teacher. The curve is equals y sine x from x is equals 0 to x equals pi over 2. To graph a sine, it should be look like this. We all know AW is equals to 1. Omega is equals to 2 pi. T is 2 pi. So this will be our 0, 2 pi. Then this will be our pi, which is x and y. And here, somewhere here, will be our pi over 2. So this part will be our area of interest, and here is our area of rotation, and this part will be our x and y, the point here. So from point here, we will draw our strip. From that strip, we will now draw our discs. That's it. This will be our dx. The height is y. From here to here will be our x. Let's extract this cylinder tin can to here. And this part will be, we'll break it that part like that. So this will be our dx, the thickness of this part. Here will be our area of rotation. Our y is equals to this. It's this part in a tin can, if you all know. X, y, the thickness of this will be r dx. Let's now go to solve the volume dx v, the integral of 2 pi xy sine xy dx. And our limit here is this, what is given earlier, since this is 0, above is pi all over 2. To solve this, we will put our constant outside, the integral of pi over 2, 0, x, and our y is sine x dx. And we will solve it to our calculator. First, let us put this in regions. 2 pi, the integral of 0 pi over 2 x sine x. Our final answer is 2 pi. That is our answer. Our last topic in getting the volume method is the washer method. This will be our a and b, this will be our limit. This will be our b, and our area of rotation is here. Stay with it, AOR. And then in this part, this will be our area of interest. From this point, this will be our x and y. We will draw a horizontal strip. And then, let's label it, this will be our dx. From here to our origin will be our x. And the height will be our y. So now we will draw our it will look like this. It's like a disc, right? It's like a disc method, what we tackled earlier, but we have a circle here, another circle there. That is the difference of washer method and this method in terms of drawing. It looks like an avocado shape. So let's extract this avocado shape here. From the middle, this will be our area of rotation. Below will be our b minus y. To solve, be dv pi b squared dx pi b y squared dx. That's it. To derive the formula, limits from a to b, pi b squared b minus y squared dx. That's it. and that will be the formula on how you will get the volume if you are using a washer method. That's it. Thank you for listening, guys. I hope you all subscribe and like my video. See you on my next lecture. Thank you.